So I'm going to talk about persistent memory, what is it? And then I'm going to spend most of my time, since this is a developer conference, on how to program persistent memory, how the infrastructure and eventually even languages may change due to persistent memory. And then lastly, I'll cover sort of physical realizations of persistent memory media. Okay, so this is kind of a trend that we've been seeing over time. And you've seen this pretty much today on from the very beginning talk. The memory is taking up more and more of your data. Storage, typical legacy storage is taking up less and less. And originally it was just DRAM and disk. SSD comes in, persistent memory, and so forth. So some of the new emerging persistent memory media technologies include, resistive RAM, phase change memory, magnetic RAM, of course 3D XPoint. Low latency NAND is sort of a new, Samsung has something called ZNAND. It's basically accelerated NAND. But you could do, basically as you go up from SLC to MLC to TLC to QLC, the latency takes a little bit longer because you're doing all these voltages like we talked about this morning. What if you took a current memory 3D NAND and ran it as SLC? Well, you could get some pretty fast response times out of today's production line NAND by running it into SLC mode. And so that's sort of a fast NAND. But of course, you're now only using 1 bit per cell. And so your capacity goes down by like 1/4. So how do you deal with these memory technologies when you treat them like memory, when you're byte accessible, right? You're no longer sending blocks down to the device, but you're actually accessing it with address lines and data lines. And that's what we'll be talking about. It really does accelerate things. It's fast like memory, and it's persistent like storage. And of course, you can treat it as a block device with wrapping software. I mean, we used to have RAM disks on the old DOS machines, right? That was persistent, sort of, while the power is on. And so you're seeing these latency sort of budgets go down as well, right? And you get to a certain point, you start thinking about, maybe I'll replace my DRAM with persistent memory instead of DRAM, volatile memory. Until recently, this was the typical stack, right? Application, file system, maybe a block driver, disk driver, SSD. And there's various ways of doing this on the horizon where you basically get rid of this driver and you have essentially a memory mapped file system, except the memory is now your storage as well. So is there even a reason necessarily to send it out to other tiers until it gets colder? And then, this completely hides the fact that you're using persistent memory from the application because he's using file system semantics. But you can enhance that by putting in this persistent memory library, and I'll talk about those, such that if you want to change your code, right, to take advantage of memory, memory access, byte addressability of the persistent memory, you can use a persistent memory library along with your file system to accelerate those parts of your application that really need this very low latency, high throughput mechanism. But eventually, we're going to actually bring these persistent memory concepts into the compiler itself, so that there's a language feature where the programmer, the application developer, has sort of a first-class concept or ability to create persistent objects. You in Java or in JavaScript or in C++, you basically create something that lives on. You don't have to stage it out anywhere. It's always persistent. So I mentioned the byte addressability, and this is from the programmer's point of view. And the key is it provides load-store access. And load-store is basically instruction sets in the CPU. Load means read and store means write, but that's the semantics in the machine language that you're actually using. And it has memory-like performance. It is memory. So you'd expect it to have memory performance. And then, interestingly enough, you can DMA and RDMA in and out of this persistent memory, which has some interesting aspects to it. Now, if you're thinking that you got page caching going on and stuff like that, when your application gets a seg fault and it has to load stuff from an SSD or, God forbid, a hard drive, your application is just spinning there waiting for that memory to fill up from wherever the data actually lives. Because it's already living in memory, you never get a page fault. And then another way to think of this is a battery-backed RAM disk or battery-backed memory. And when you get to the physical device, it is battery-backed. Kind of. So how do you write an application for persistent memory? Well, the SNIA got together and we got the stakeholders from folks like the Linux community, the Windows developers, kernel programmers together in our technical work group, and we came up with this is the semantics that we have to propagate in the whole storage stack in order to make this stuff work. So we came up with the NVM programming model. It's up to version 1.2. You can go out and get it. We released that latest version in June. We're now working on the next version of it, but the goals we had was to make it application-centric, of course vendor neutral because we're SNIA, and make it so that it's achievable today, and it just goes beyond storage, beyond networking fabrics, and presents that sort of cohesive view that everybody's going to adopt. So we want to accelerate the availability of software that makes persistent memory hardware available. The early applications when persistent memory just first became available were to sort of map it into the semantics that they already had applications programmed to, right? Block devices and file devices. We cover that, but we also cover the future and a different way of doing it. So what we do is we describe the application visible behaviors. We don't actually have an API. It's not an API. However, when you land on Windows, the API that Windows gives you is based on this model. When you land on Linux, the API they give you is based on this model. And so that was the idea. It didn't need to have a sort of cross-platform API. What we wanted was the semantics and the ways these things work to be common across those. So here's the way to get the standard. We're working on different aspects as we go forward, but we do talk about Atomicity. What is the capability of Atomicity? What does it mean both on the local machine and when you might have remote access? We talk about the use of memory map files for persistent memory. That's that second column where you have a file system that completely hides the fact that you have persistent memory. And then I just mentioned the programming model, not an API. So these four kind of modes, if you will, are what we're talking about as far as your typical block mode innovation, where you make this memory, even though it's byte addressable, you make it block addressable because that's what the applications are for. And you can get significant performance improvements from applications that are not rewritten to use persistent memory. But if you're willing to go all the way over to this column and actually use the semantics that are byte addressable, you can really speed things up. So the file and block modes use I/O, right? It's not a load store thing, it's I/O. So you're reading and writing RAM buffers, and the software controls how you're going to wait. Are you going to context switch when you want access, or are you going to sit there and poll? And it depends on how long you expect to wait, right? The status is explicitly checked by the software. And then to go to the next stage, the nvm.pm.file and nvm.pm.volume modes enable that load store. So data is loaded or stored from the processor registers. Processor makes software wait for the data using the instruction, right? There is no status check, right? But you will have to be able to handle exceptions just like you do today. So here's it graphically, right? Block aware has block mode extensions. You wrap the byte addressable device with a block addressable driver, and then you can build file systems on it. You may have extensions for things like flush, optimized flush. I'll talk about those in a minute. So when you're talking about the persistent memory modes, the PM volume mode has a software abstraction for persistent memory hardware. And instead of, yeah, it's a volume, but you have address ranges. And then, so maybe you don't use the entire address range you need. You could thinly provision the actual memory device into the address space that you're actually using right now. So this allows the persistent memory aware application to map, to grab some of that address space and say, okay, that is assigned to this persistent memory device. File mode is application behavior for mapping PM files to the application address. So you open a file with the open, and then you map the file to some persistent memory, and that is handled by the file system, the allocation, deallocation, and so forth of that, that memory for that file. And then syncing becomes an issue, and we'll talk more about that. So map and sync. Map associates the memory addresses with that open file. And then you can also request specific addresses because, again, your data is sitting in that persistent memory. And you created it maybe weeks ago. And so what you want is to be able to go back and use that exact same location in that memory and map it into this file that I just opened. Now, sort of truism is that with the load store is that you're reading and writing from memory, but you're not. Your CPU never actually writes to memory. It writes to its own internal cache. And, and so when you write and you think you're writing to persistent memory, what you're actually doing is you're writing to cache. And it's backed up to persistent memory. Not really backed up, but it's eventually flushed out to persistent memory, right? So that's where sync comes in, right? You want to flush the CPU cache for this address range, and you want to make sure it actually lands down on the persistent media, right? And so we have a bunch of different sync types that we've defined. It could be that at the time you get into doing the actual flush, the memory management system, the DRAM refresh circuitry has already got it out there. So what you want to do is if it is already out there on the persistent media, it returns immediately. That's why you call it optimized flush. And really, there may be multiple failure domains as well. There might be some amount of power protection or power loss protection in the CPU complex and some of the DRAM and further out. So really you want to just flush it to the point where if the power goes out right now, then you're still safe. And that may include while it's still in the cache. Now, one of the caveats is that sync does not guarantee the order of how it gets out there. So you may need to think about that in your app. Parts of the CPU cache may be flushed out of order, and that may even occur before the sync action is even called. The sync is even called, right? So all that sync does is it guarantees that all data indicated range has been flushed at some time before you return from that sync call, okay? And then failure atomicity is sort of, today what you have is atomicity that guarantees inter-process consistency. And that's a symmetric multiprocessing concept, right? But only provides limited atomicity with respect to failure, power failure mainly, right? But not just power failure, system reset, restart, crash, you know, somebody may be coming in and about to reset your whole system. The cloud may be right about to move you to another physical machine. And there are such things as memory failure as well that you have to worry about. So failure atomicity itself is going to be processor and CPU complex architecture specific to a lot of cases. So processors will provide failure atomicity of sort of the aligned fundamental data types. And this is to help the compilers with their concept of what atomicity means. So what we mean by fundamental data types is pointers and integers. Pointers for sure, integers, and maybe D words, and who knows what. And then the persistent memory programs can use these to create larger atomic updates or transactions. Did I get to the point where I thought I got to, kind of thing. And then to fall back, you might have your own CRC or checksum with your data, so that you basically saying, I don't trust the processor complex, or I want this to work on multiple CPU architectures, not just the one that I'm running on right now. So we've got the programming model, which specifies these NVM interfaces between the OS components. We've got application interfaces to non-volatile memory related OS, hypervisor, and hardware components. One of the things that we started worrying about was, so you've got your data on the persistent memory on your machine. That's durable. If power goes off, your data's still there, but nobody has access to it. If you want it to be highly available, you don't only have to persist it on the local machine, you want to persist it somewhere else. And so we did this white paper on remote access for high availability. Go look at that. It talks about all these considerations. We're still digging in this space, and we may end up working with some other groups to help us solve this problem, like the Open Fabrics Alliance, for example. And we're looking at basically persistent memory over fabrics. May not end up with that name, but that's essentially what we're digging in. We're going to re-dig in it some more going forward. Asynchronous flash persistent failure, describing the considerations for supporting atomics and transactions using extensions. We also have sort of work in progress of persistent memory security for multi-tenancy. And this is important if we want to see persistent memory uptake in the cloud, because now it gets a little more complicated. You've got multiple tenants putting their data on the same physical device. How do you do that? How do you protect against that? Do you encrypt data at rest? Do you encrypt it on the CPU before you send it to the NVDIMM? You encrypt it on the NVDIMM once it gets there? Do you have a key per user? Anyway, we're working with people like JEDEC and Trusted Computing Group And this is our way of sort of saying, well, here's all the different threats that you have to take care of eventually with various things. What happens today? Well, a hyperscaler is going to shred the persistent memory before it leaves the data center. Why? Because it's got customers' data on it. And it ends up on eBay and somebody reads the data, you're screwed. So we'd like to have something, stuff in place so that the data center owners don't have to shred these persistent memory devices when they leave the data center. And that's only if we can cryptographically secure the data that's on there, such that that's not needed. So in summary for the model here, it's aligning the industry around these things. If you go to pmem.io, you'll see some of the libraries I was talking about, as well as pieces of kernel that have been put upstream. There's something called a DAX-aware file system in Linux. Look for FSDAX. There's a Linux PMEM examples in this GitHub location. We're continuing to develop new work items. We're looking at some of the things to go forward. And there's going to be emerging technologies that drive increase in the work in that area. And as the cost comes down, the latency comes down, and so forth. So let me just drill down for a couple minutes into what this actually looks like, what physically looks like, right? And the current sort of instantiation of persistent memory out there kind of looks like this. And the NVDIMM-N is a connotation from JEDEC about this particular architecture, right? So this plugs into the memory bus just like a DIMM, and you access it at memory, full-on DRAM, DDR memory, because there is DRAM on the card. And so your computer, your application's writing to the DRAM, and what if the power fails? Well, either via supercaps, batteries, or external power from a battery, what happens is this thing knows when the power is going down, and it takes all this DRAM and dumps it into the NAND flash in sort of previously arranged erase blocks. What you don't want to do is do garbage collection and erasing while the power is coming down, right? So you make sure there's a bunch of erase blocks in here already ready for this amount of data. And as soon as the power comes down, you're writing quickly all this DRAM into the NAND flash before the battery wears out. Now, this is not cheap. You're paying for the original amount of DRAM that you would if you just had a DIMM, plus you're paying for an SSD, plus you're paying for an NVDIMM controller, plus you're paying for batteries. So this, currently these are only going in where there's a specific use case for this kind of very high performance that will justify paying this cost, right? But over time, we're going to get actual persistent memory technologies, like I showed at the beginning, that will act or work closer to DRAM speeds, maybe even eventually DRAM speeds. Part of the standards that are coming up are in the area of, can we get a memory bus standard that will slow itself down to match whatever the persistent memory media is capable of now? So maybe when you access persistent memory in the future, it won't be a bunch of DRAM fronting it. It'll just be that media, since it's already byte addressable anyway. It'll just take a little bit longer, maybe 1x, 2x, somewhere in there, maybe up to 10x. And so even though your application will slow down when you're using persistent memory, that kind of persistent memory architecture, it's still a heck of a lot faster than the 100x you'd get with a standard NAND. So there are different types. NVDIMM has DRAM flash controller, but there's also this NVDIMM-P where there's a media controller here, and persistent memories and high-capacity DRAM on DDR and DDR5. It extends the DDR protocol to enable transactional access. So the host is essentially decoupled from the media, and then you can support multiple media types. And this is the key here, is it supports any latency from nanoseconds to microseconds. So your host kind of like adjusts to whatever actual persistent memory is actually on the car. Some of the applications we've seen is in-memory database. In-memory database, if you can speed them up 10x, 100x, you really can justify paying that extra price. But even traditional databases, enterprise storage for certain applications, VMs, I talked to one hyperscaler that wants to use the persistent memory to increase the number of virtual machines it can run against any physical CPU. If I can go from 20 customers on one CPU to 100 customers on one CPU, that's a big win. Use case is pretty much what I already showed you. Linux 4.4 Plus has NVDIMM OS support in it. And so looks for XFS DACs, ext4 DACs, and this is direct access. DAX is direct access. It's the same thing that Windows calls it too, I believe. But this even allows you to have a PMM address space actually span a interleave of several DIMMs. And then Windows Server 2006 supports this DDR4 NVDIMM block mode, not the NVDIMM-P yet. But the nice thing is you don't have to change your code. You just get a much faster device. And you still have access to the overhead of the I/O path. And again, Windows calls it DAX, but they call it NTFS DAX, of course, because you're using the NTFS file system. But you don't have to use I/O. There's no queuing. There's also async reads and writes. And here's where you go to find out more about the NVDIMM-N support on Windows. Here's a Windows example. This is Tale of a Log in SQL 2016. And so that's the summary. PM mode is really what you want. All the PM modes are where you really want to go to. That's it.